Thanks. But we could have done anything, and the only thing that we could have used anything. The only thing that is important is that we have some total order over the things that we're comparing, so that we can always say one thing is less than or greater than another, and this total order should obey the rules that a total order should obey. It should be transitive and irreflexive or something, whatever the normal rules are, but whatever you think of when you see the less than sign. And so that means that when we're searching, or when we're searching in this structure, there's a thing we're searching for, and there's something we're looking at in the structure, and we have to make these decisions, and they're always based on taking the thing we're looking for and comparing it to something in the structure. And there's only two outcomes, right? If it's a comparison of the form, is A less than B, the answer is true or false. Okay. And we could imagine more complicated things where we do even more sophisticated comparisons. Let's say we're searching for X and we have A in the structure. We could ask something like, is X plus 2 squared bigger than A to the power 4? That's another kind of comparison, but it still only has two possible outcomes. It's either true or false. If we think about it for a little bit, then we realize, well, if we do a search in some set of n elements, and we're doing the usual search that's supposed to return, in the literature, it's called the successor search. When we search for X, we want the smallest value in the set that is bigger than or equal to X. Then if we have n elements, we have n plus 1 possible outcomes. And that's because n numbers partition the real line into n plus 1 intervals. Two of them are infinite intervals at either end, and the other ones are finite ones. And so there's n plus 1 possible outcomes. And whatever we search for, each of these outcomes is a potential answer, right? If I search for 3.5, well, then I should, this is the answer that I'll get is 5. If I search for 17.2, well, then I'll get 102. If I search for 2000, then I'll get null or infinity or whatever you're supposed to return when you're in that interval. So there's these n plus 1 possible outcomes. And now, forget about, I mean, it's okay to think about binary trees, but kind of step really far away from it and just think about what a search is doing. It runs for a little while, and it does somewhere in the code for that thing is an if statement that says, if some condition, which is either true or false, do this, else do that. Okay, so the first time there's a branch in the code like that, a binary branch in the code, you can think of, well, the algorithm, the condition that it tests is either true or false, and if it's false, the algorithm executes one way, and if it's true, the algorithm executes another way. And this algorithm has to have n plus 1 different executions if it's going to be correct, because n plus 1 different things that it has to return. So if you sort of keep imagining this thing, well, let's say that the first condition that it tested was false, well, then it's going to go for a while and it's going to test another condition, which is either going to be true or false. And if that one was false, it's going to test another condition, which is either going to be true or false. And eventually, let's say all the conditions it tests are false, then it decides, oh, okay, now I know the answer, it's this thing. And you can back up and say, well, what if that last condition it tested were true? What should it do? Well, then maybe it has to do some more tests, but eventually it knows the answer. Maybe it's a bad algorithm, and sometimes it has two ways to the same answer. That's not important. But what is important is that it should have, n plus 1 different answers. Okay, so I don't know, maybe that's what this is what's formally called the decision tree for this search process. And well, it has to have n plus 1 different leaves, at least, possibly more if it's not a particularly good decision tree. And well, it's a binary tree, so each node only has two children. So that means that its height, which is the length of the longest path from the root to a leaf, has to be at least log n plus 1. Log base 2 of n plus 1. Okay. And there's nothing we can do about that. If we're looking at these kinds of algorithms, if there's n possible outcomes or n plus 1 possible outcomes, some of those outcomes will require us to make log n plus 1 of these decisions at least. And we've played around with that a little bit when we say, well, some of these outcomes are more likely than others, in which case we can somehow make the path to those outcomes shorter, but that comes at a price because there's still other outcomes that are less likely, and the paths to those have to become a little bit longer. Okay. So, but so sort of no matter what, in the worst case, there will be something you can search for that will require at least log n plus 1 steps. And that's not just because you're doing comparisons, it's because you're working with an algorithm that makes binary decisions where there's only two outcomes. They could be comparisons, they could be coin tosses, they could be whatever. It doesn't matter, as long as there's only two possible outcomes, that's going to have to happen. Okay. So what I want to start looking at now is a class of data structures that does better than this. And we're going to see a few of these, and for different kinds of problems, and see some really nice tricks. But what all of these data structures have in common is that they find some way to do one operation that has way more than two possible outcomes. So that's going to be the trick throughout, doing something that has way more than two possible outcomes. So, can anybody tell me what one such operation is that computers do all the time? Pardon? Something that affects the execution of a program in a way that in sort of constant time, many different things can happen, not just two. Yep. So the result of a hash function, yeah, so that when you hash a integer or something, well, it's a function, so you get, there's actually no branching at all. So you get something back without, there's sort of no branching that happens at that point. But what do you do with that thing that you get back typically? You use it as, you use it to choose what? Yeah. A what? A storage location. So you use it as an index into an array. Okay. So somebody gives you something that you're searching for, you do something with it. In this case, it's you hash it. That gives you some integer I, and then typically then what happens in a hash table is you've got an array and you go to position I in the array and do something, either search for the thing you're looking for or add it or whatever. But so think about what this does to the state of the machine. When I hash like this, so I have this data, I do something in constant time, depending on the data, maybe I get any one of these, I don't know how big this thing is, m, whatever the data is, maybe some number comes out that's between 0 and m minus 1, and now I go and change something, change or even step to that memory location in this array. Okay. So that's an operation that takes constant time, but has m possible outcomes. So the state of the algorithm, in particular, if I change the value here, then the state of the algorithm is different for each of those possible outcomes. That's something that doesn't happen when you do binary comparisons. Okay? So this will always be the trick. Keep this in mind. The way to beat this log n bounds, and this is log n bounds for searching, but it's also, for instance, if you're sorting, if you want to beat n log n time bounds for sorting, you have to do this similar thing. You have to do operations that have many possible outcomes that only take constant time. And sort of the standard one is taking something and using it as an index into an array. Okay. So let's we'll revisit the classic operations. Insert. So maintain a sorted set. Add, and I'm going to call it successor, but the name keeps changing. I think I may have called this find or search. This one here is return smallest value in the set that is greater than or equal to x, the value that you're searching for. Okay. So these are the classics. And of course, you know, in addition to successor, you can also have predecessor, which is this finds the value that comes after x, predecessor finds the value that comes before x. And we want to do this fast using arrays. So I already argued that actually, if you're only doing making binary decisions, then even if you don't support adding, inserting, and sorry, why did I say insert and add, insert and remove? Even if you don't support these two operations, you just want to store a bunch of stuff, then if you're only making binary decisions, it's still going to take you log n time, where n is the size of the set you're storing. So let's just try and make sure we can beat that. Don't care about adding and removing, and I don't care about the space that I use. Okay. So what's the catch? Well, I need to say something about what kind of items are in my set. So they have to be something that are not just opaque things. They have to be something I can manipulate, maybe do arithmetic with. In particular, they have to be something that I can turn into array indices. So what's better than that is, or what better than integers? And let's just say we store a subset of the integers 0, 1, 2, and so on, up to some big number n minus 1. And I'll use a capital N to say that this is a big thing. And we'll see really big. All right, so, well, let's say you just give me a subset of these numbers, and you want to build a data structure. You don't care how big it is, but you want to answer these queries as fast as possible. Can someone tell me what to do? Yep.
You can just make an array of size that has 1.
It's actually an array of size n because of the 0, but that's okay. And we have some elements that are in our set and some elements that are not in our set. So we can take, let's say our set is going to be x1, which is less than x2, which is less than so on, which is less than xn, little n now, so it's a small compared to the size of the universe. Well, we can go to position x1 in the array and set all these values to x1. Then we go to position x2 in the array and set all these values to x2. And then x3 and set all these values to x3 and so on up to xn. Okay. Now I come along and I search for x, and these numbers here, I can really say explicitly what they are, so no one's confused. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So I come along and I want to search for some value x. Maybe x is 11. I go immediately to position 11 in the array. That's right here. And I read off the value x3, which is 12. The answer is stored right there. So really, really simple. And it definitely beats the log n lower bound. This is just one array lookup. Clear? Sort of dead simple. Now, what if we want to add or remove things? Is this a good solution? Yeah.
Is x supposed to be an actual value, or is it
X is an integer that we're searching for, but integers can be used as indices into an array. So what we're storing is some set S, which is a subset of these integers. In this case, the set S is 5, 9, 12, and 14. And you search for some value. In this case, you search for the value 11. Just it happens that the way that I've implemented that is I have an array of length n. And the way I implement the search is I just go and look at the array position where the answer is stored for that particular value. Okay. And this works because there's only n possible things I can search for. So I can literally store every possible answer. And in fact, this would even work if you could search for things that were not even integers, but real numbers, because you can truncate them. As long as the things that are in your set are only integers, this would work too, right? If I search for 11.5, well, then I would just take the floor of that and go to position 11 and find the answer there. Or 11 or 12. We'll take the ceiling, I guess. Okay. Now, what if I want to insert or remove things? Is this going to work well? Doesn't look like it, right? Yeah, so the problem is, I mean, this is not an indicative example here, but n, I mean, a small value of n is 2 to the 32. That's just 32-bit integers. That's 4 billion of those. That's a small value. Another reasonable possible value of n is 2 to the 64. 64-bit integers are extremely common. All our laptops and desktops easily do arithmetic on those things. No reason we can't store them. You could have n is 2 to the 128. That would be something like IPv6 network addresses. Or if it's some cryptographic application, you might even have n is 2 to the 2048. Okay.
Wait, shouldn't that be 31? Because if you have 32 bits, then the maximum power is 31.
Well, for unsigned integers, they
Okay.
will be between 0 and 2 to the 32
yeah.
minus 1. Yeah. Or even this. So there's a few problems then with this kind of solution. Well, one of them is memory-wise, it probably doesn't work for any n bigger than this. This is about 4 gigabytes, an array of, well, an array with 4 billion entries, and if each one is 32 bits, that's another times 4. So it's like 16 gigabytes. That's all the memory on your laptop used to store this thing. And all of these are just not doable that way. So memory is a problem. We like that to be smaller. And the other is the updates, right? If I now say something like add or insert 4 into this data structure, well, then I have to go to position 4, that's here. And I have to change all the answers which need changing, which means I need to put 4s in all these places where there were these x1s, and that could be a lot, right? In fact, that could be 4 billion entries just to add one element. So not so good. Yeah, so this just illustrates that we can definitely do faster. We can beat lower bounds trivially with easy data structures. But now let's try and make something that's really going to be fast for all 3 of these operations. So, so I'm going to present today a famous structure called the Emde Boas heap or Emde Boas tree. This person here, Peter Emde Boas, has a Carleton connection. Anybody know what it is? No. He was a supervisor of a professor in our department. I'll let you guess at which professor it is. He came up with this thing in the 1970s, and it's a nice, elegant example. We'll see next class there are better solutions by now, but I really like it because it pieces things together in a really beautiful way, where all of the pieces just fit perfectly. And it illustrates also the sort of, well, one of the recurrences that's useful. So it's based on this recurrence. And T of, it's not really important. So it takes our problem of searching or adding or removing from a universe of size big N. And so we're going to have to do 3 algorithms, one for inserting, one for removing, and one for searching. And the way that they're going to work is they're going to do a constant amount of work. And in addition to that, they will recurse on a universe which is a size smaller by a factor of by square root n. Okay. And another way to write square root n is n to the 1/2. And when you do that, you can see what this thing does. So you get a constant plus t of n to the 1/2. If we expand this thing, we get a constant plus t of n to the 1/4. If we expand that thing, we get a constant plus t of n to the 1/8. And we can keep expanding this way. How long will this go on for? What exponent do I need here before this thing is of constant size? Yeah, so what I need, well, this will stop when I get down to something which has size t of n to the 1 over log n. Okay. Why is that? That's because n is equal to 2 to the log n. So, well, that means that n to the 1 over log n is 2 to the log n over log n, which is 2 to the 1. Okay, so we stop when it's 2, I guess, not 1. Okay. So whenever this exponent drops to 1 over log n, that means we're dealing with a universe of size 2, which is easy to deal with. But this exponent each time it starts out at, it starts out at 1, and then it goes to 1/2, 1/8, 1/16, and so on. So the exponent is decreasing by a factor of 2 each time, which means the time it takes, the number of steps before it gets to log n is only log n. Okay. So this recurrence resolves to t of n is O of log n. Now, if you look at these numbers up here, log n for 2 to the 32 is 5. This one, 6. This one is 7. And this one is 11. Okay. So huge numbers, 2048 bits long. And these things will be able to find them, find numbers from that set in basically 11 steps. And that doesn't matter how big the set is. So, I mean, this is way more than, I don't know, the number of atoms in the, it's not even comparable to the number of atoms in the universe, for example. So, okay, good. All right, so this is what we're shooting for. A recurrence that somehow we do constant amount of work, and then we recurse on one thing on a universe of size square root of n. Okay, good. And for Van Emde Boas trees, we're not going to worry about space because we'll see later structures that do same performance with better space. So we won't care if we're using big arrays, although you can get around those big arrays using hash tables, but we'll not worry about that for the purposes of this lecture. So it's a tree, as the name suggests, and it's going to be not a binary tree, because a binary tree doesn't sound like it's going to work for us. So at the root of the tree, this is where our searches start. And we're going to be searching for something that could be anything in this universe of n, big N elements. And it will be, what we want is, well, we do something at the root, and then we suddenly get down to a universe of size square root of n. So we should decide how many children the root should have. Yeah. Log n won't be enough. If we have only log n children, then one of them would have to be on a universe of size n over log n. Square root of n. Okay. So we're going to take this thing so that it has square root of n children. Okay. Now, very roughly, what's going to be here? Well, this is going to be a tree that we will go to if we need to, if we are searching for something in the range 0 up to the square root of n minus 1. That's what the first child is. The next one, if we're searching for something in the range square root of n up to 2 times the square root of n minus 1, that's where we'll go. And then finally, the last one will be finishing at n and starting at n minus the square root of n plus 1. Oh, no, n minus 1, yeah. N minus the square root of n. Okay. So this just breaks the universe up into equal size pieces, each of size square root n. And to make our lives simple, we will do like all our examples, and we'll assume that n is equal to 2 to the 2 to the m for some integer m. That's what all these are, right? This is a power of 2, so is this, and so is this. The only reason to do that is so that we can keep taking square roots and always getting integers. All right, so that's the plan. So the root, we'll call it w as square root n children. So we'll call that, I don't know, w dot child at I, and that's for 0 up to the square root of n minus 1. Okay. So that's one thing, one way to describe it. Now, like I said, this structure is full of really clever ideas that fit together in a really tidy way. So this is not such a clever idea. I mean, once you know you're aiming for this recurrence, then that's sort of what you have to do. Another sort of what seems like a small idea is we will also have w dot min and w dot max store the smallest and largest values. Okay. So that seems like not such a big deal. Whatever the smallest value in the set is, we remember it. Whatever the largest value in the set is, we remember it. And that's at the root. But, and this is important, these values, these two values are not stored in any children. Okay, so for example, if the set that you give me only has two values, 5 and 7, then you'll have w dot max is 7, w dot min is 5, and nothing else happens inside of these trees down here. That smallest value is only stored at the root, and the largest value is only stored at the root. It's not stored recursively. Right. There is a tree here that should store the value 5 or the value 7, but it's not there. It's only stored at the root. Okay. Simple stuff. And then finally, and this is the very clever idea, we have something called the auxiliary structure, w.aux. Okay. So it stores the indices of the non-empty children. What is w.aux? This is the extremely clever part. This is a Van Emde Boas tree over the universe, 0 up to the square root of n minus 1. Right? If I look at this thing, I said I have square root n children. They're called 0, 1, 2, and so on, up to the square root of n minus 1. Some of those children actually have a value in them, and some of them don't. The ones that have a value in them, well, there's a set of these integers where that child has a value in it. That set I store in the same kind of data structure on a smaller, on the smaller universe, on a universe of size square root n. And then, of course, each of these things is a Van Emde Boas tree on a universe of size square root n. Okay. So the trick is going to be making sure that we can maintain all this stuff so that during, well, the one trick is to make sure that this lets us search. We'll have to check that works. And then making sure that we can maintain all of these things while only ever having to recurse on one structure. Okay, so we can never do something, and this would be sort of the natural thing to think of is, okay, well, when I go searching for a value, I might say, if I search for x, well, then what I can do is take x and divide it by the square root of n. That gives me the index of the child that should store x. Of course, so I could search in there. That would be one recursive search. But then maybe there's nothing in that tree that's bigger than x, in which case that search failed. But that doesn't mean there's nothing in my whole structure that's bigger than x, because there can be something in the next tree, or the next tree, or the next tree. And then you say, okay, well, I can use aux to find out which of those next trees I should go to immediately. But already now you're in trouble, because you did a search down here, and you did a search in aux. That's two searches in two things of size square root n, of universes of size square root n. That's not this recurrence. This recurrence has a 1 in front of this t, an implicit 1. Okay. So we got to do this carefully. So let's do the search. Just so that I don't forget anything, I'll refer to my notes. All right. So I have this tree, and I want to search for, I think we can remember this recurrence. Write it down here. All right. So let's just try and build it ourselves. I want to search for x. And let's try and do the easiest things first. What's the easiest thing to check first? Pardon? I didn't catch it. I mean, let's say you start hacking and you just start writing, writing code and saying, well, what kind of queries can I really easily answer? Yeah. Is it smaller than min, or is it bigger than max? If it's smaller than min, I know the answer. If it's smaller than the smallest element, then the answer is the smallest element. And if it's bigger than the largest element, then the answer is infinity, or no answer. Okay. So we can have something like if x is less than, so we are searching for x in the tree rooted at w. So if x is less than w, less than or equal to w dot min, then we return w dot min. Okay. And if x is strictly bigger than w dot max, then a return I don't know, infinity, something that indicates that there's nothing in the set that's bigger. Or actually what you should return is n, because that's bigger than anything you're allowed to store in the set. That's like infinity. Okay, what else is easy? Or if that's not the case, what should we do next? If it's equal to the largest one, yeah, we can do that. I don't know that we'll need to. Oh, maybe we can. Let's make sure we catch that. Okay, so none of those things happened. We have to, we're going to have to do something non-trivial. And maybe I should point out one little convention. So I said w.min and w.max store the smallest and largest values. I didn't say what happens if there are no values in this tree. And I didn't say what happens, well, if there's no values. So let's use the convention. If the tree is empty, then we'll do something like w.max is equal to -1. And even w.min, just something that doesn't make sense otherwise. Something so we can tell if the tree is empty. So in this case, if the tree is empty, w.max is -1, so this will return infinity. There's nothing in there. You're set. Yeah. What we're storing in the auxiliary tree, so some of these subtrees have things in them, and some of them don't. Right? Maybe this 3 have things in them and the rest are empty. Then in the auxiliary tree, so this is tree 1, this is tree 3, this is tree 5. In the auxiliary tree, we are storing the set 1, 3, 5. The indices of those children that have something in them. Yeah, this is the same kind of tree. This is a Emde Boas tree on the integers 0 through the square root of n minus 1, which is the names of these children. Yes?
So in the case that x doesn't fall into one of the above cases,
Yep.
the second constant time one of the tree exists, then using those requirements.
Okay, good. So let's figure out, I mean, X should be there, so it's not the max, it's not the min, the tree is not empty, that would all be over by then. So X itself, if it was there, is going to be in some particular tree, and it's going to be in the tree at index like X over the square root of n floor, I guess. Okay, so that's where X should be if it's in there. All right. Yeah, okay. So we now know if X is there, it should be here in this tree I. Now, we have to be careful here because we don't want to make two recursive calls, or if we do, we better make sure one of them runs faster. So we should decide whether we actually want to look in that tree ti, that ith child. Okay. And how do we know if we do or not? Well, that ith child, where X is supposed to be, it has a value, a maximum value that it stores. It's right there at the root of that ith child. And if that's bigger than X, then we know that the answer we're looking for is somewhere in that ith child. It may or may not be the maximum value, but definitely the answer is in here. Okay, so we say if W dot child at I dot max is bigger than or equal to X, then we return successor of X in W dot child at I. Okay. Now, if X is bigger than the maximum value in that tree, then we know the thing we're looking for is not in there. Okay, because everything in there is smaller than X. So maybe it's in tree I plus 1, maybe it's in tree I plus 2, maybe it's in tree I plus 3. Well, that's a lot of things to look through before we find one that's non-empty. Luckily for us, we have a data structure which will tell us what is the next non-empty subtree. Okay. So otherwise, we can say I gets successor, and I guess we want to search for I plus 1. So we know the answer is not I. We want to look from here onward in the auxiliary tree. So that gives us a tree. It stores values that are all bigger than X, and it stores at least one value. Okay. All right, so this was one of those recursive calls. Now we have to finish up and make sure we're done immediately without another recursive call. How do we? Yeah. So we return W dot child at I, that's now the one we want, dot min, right? Everything in there is bigger than X, and so we want the smallest thing in there. That's the smallest thing that's bigger than X. Nothing happens before that because all those other trees before that one are empty. So let's see what we get here. This is all constant time stuff. There's one recursive call, but if we make this call, we're done. And otherwise, we didn't make this call. Here's one recursive call. So we only make one of these two. And then after that, we're done. So that satisfies this recurrence. Constant amount of work in all the other lines, plus one recursive call in either in aux or in the ith child. Yep.
Take that, I in the first line actually existing, and so that already do the recursive calls.
Well, we here, you mean?
No, 2 lines up. So that's the first line.
2 lines up.
What do you think of that?
This one?
Yeah.
No, I mean, we're assuming that somebody gave us a valid number x, which is an integer in the range 0 through n. So when we divide it by square root of n, we get an integer in this range, 0 through n minus 1. So these children are all there. So we're not going to worry about space for now. We just assume all of these things are built. But I mean, if you don't want to do that, and I mean, in reality, it would be silly to have giant structures for empty children. You would check. I mean, instead of immediately looking at the max value, you'd check to see if that thing is empty or not. But the code is already going to get long enough without having to worry about those things. Okay, good. Successor, good. Log n time. So even for a universe of size 2 to the 2048, that's basically 11 recursive calls. All right. Insert. Okay. Now I want to insert a new value x into the tree that is rooted at W. So again, what's sort of easy? What's the easiest thing that could happen? Pardon? It's empty. Yeah. So if W dot min equals W dot max equals -1, then the tree is empty. And the rules say we need to store x, and x is going to be the min, and it's going to be the max, and it only needs to be stored right there at the root. So then we do W dot min gets W dot max gets x. It's both the minimum and the maximum value. Good. Okay, let's leave that like that. All right, what's the next easy case? If what? Yeah. So if W min equals W max, but they're not both equal to -1, that means our tree has one value in it. And now we're inserting a second value, which is either going to be the min or the max, but that's going to be another easy case. So then we just do something like W min gets to be the min of W min and x, and W max gets to be the max of W max and x. And in that case, we're actually also done. And this even works if x was the same as those two, if nothing changed, if x was already there. All right, so now we're getting down to the meat. What's another special case? Yeah. Oh. If x is smaller than the min, then what happens? Then we should swap x and the min. Why swap them? Well, if x is smaller than the min, then x is going to be the new min. But we're not done yet because the current min, before we had x, is stored here at this node and only at this node. X is now the new min. That min has to go somewhere down there. Okay? So that's why we swap them, because whatever code is coming next is going to insert x. All right, and then there's, of course, symmetric case where if x is bigger than w dot max, then we swap x with w dot max. Okay. And then finally, let me just, I don't want these things to bother us. So if these two easy cases happen, we just get out of there right away, just to make sure the code is correct. Okay, so now we're really at this place. We have this value x. Maybe it's the original one, maybe it's the old max, maybe it's the old min. It needs to get inserted somewhere. Well, we know where it needs to get inserted. It needs to get inserted in the ith child, where you get I by dividing by x by square root of n. All right. What now? All right, so let's insert x into w dot child at I. Sounds good. Are we done? Okay, so we're not done because we have what has now become an annoying ox structure, which is supposed to keep track of the trees that are non-empty. We just inserted into the ith child. We didn't check if it was empty or not empty before. So it could have been empty before, in which case it's now non-empty, in which case the value I needs to go into ox. So we can check after the fact or before, it actually doesn't matter. If w dot child at I dot min equals w dot child at I dot max equals x, that means x is the only thing in there. We just inserted into an empty tree. We need to insert I into the tree ox. Okay, so let's analyze it. Constant time, constant time, constant time, constant time. Recursive call. And then a possible recursive call. That looks bad. Two recursive calls, we're not supposed to do that. But let's think about it for a second. What happens if we have to insert I into ox? That's because this ith child used to be empty, now it's not. But if the ith child used to be empty, then when we inserted x, this is what happened. These two lines of code executed and then it returned. There was no real recursive call. This is just constant time. In fact, we could have pulled that check out here just to make it really clear that we only make one recursive call, but we don't need to. Okay. So if this one is a real recursive call, which we actually have to insert I into ox, that's because this one was done in the first two lines of code without any more recursion. Okay. So there's really only one true recursive call. If this is truly recursive, then this doesn't execute, and if this executes, then this was not truly recursive. All right, so that does insert. Only one left to do. remove X from the node W. Again, let's start with the easy cases. So the easiest case for insertion was inserting into an empty tree. So what's going to be the easiest case for deletion? Deleting the last element from the tree. And we can detect that if W, this whole tree, only has one value in it, and it's X, then that value is only stored at the root in the min and max. And we'll be lazy here and assume no one is asking us to remove something that's not there. That wouldn't, I mean, we could always check for that, but you see I don't have a ton of space on the board here for this. So if that happens, you're just removing the last element, then you set these things to indicate that the data structure is now empty. Set them both to -1, and I'll say return. All right. What else? Well, the parent deals with that. So this is the root. I mean, our view of this is the root. If there was a parent calling us, and we will be the parent at some point later in the code, we'll deal with getting rid of it in the auxiliary thing. We're responsible for our own auxiliary thing, not the parent's one. All right, so that was deleting the last element. What else? Uh-huh. Even before that. So we actually saw when we were inserting, there was another special case where we inserted into an empty tree. There was also a special case where we inserted into a tree that had only one element. So the inverse of that will be removing from a tree that has only two elements. How do we know if our tree only has two values? So if our tree only has two values, they're stored in the min and max, and they'll be different. But every tree that has at least two values are stored in the min and max. What's that? Yeah. So if we only have two values, they're stored at the min and max, nowhere else. In particular, no child has anything in it, which means the auxiliary tree is empty. So the way we can check that is to say if w.aux.min equals w.aux.max, this is a bit redundant, equals -1. The auxiliary tree is empty, meaning there's only two values in our tree. They're stored in the min and max. There's not only one value, otherwise we would be done already. So we just need to deal with that, and that is boring. I don't know. If x equals w.min, then w.min equals w.max. X is going to go away. Otherwise, w.max, so x is equal to w.max, then w.max gets w.min. Okay. And we don't have to touch the auxiliary tree because nothing was removed from it. All right. So that's the easy stuff. Now what? Still more special cases. So now we know that the thing has more than 2 values. Well, still, before we do that, there's still some special cases. Yeah. Yeah. So if x is equal to w dot min, then, well, a couple of things are going to happen. That needs to go away, and we need to find a new w dot min. And how do we do that? Yeah. So if x is w dot min, we're deleting the smallest value. We need to find the second smallest value. So we go into this auxiliary tree, which will tell us the smallest indexed child that has something in it. We find that thing, and the smallest thing in that is the smallest thing overall. Okay. So let's find the index of that thing. That is, if x is w dot min, then we do j gets w dot ox dot min. That's the smallest child. That's the tree with that's not empty. And then we want w dot min gets the smallest value in that tree. So that's w dot child at j dot min. Okay. Now that value is now stored up here as the min value, and it's also stored in that child below. We need to get rid of it. Yeah. No, w dot ox dot min is the smallest. It's the first tree that has something in it. Okay, so that's that first tree with something in it is going to be, it's that smallest thing in that tree. What we're getting here is the second largest value in the whole set. So it's second smallest value in the whole set. The smallest value was w dot min, the one we're deleting right now. Okay.
The minimum of the auxiliary is not the same as the minimum of the trees.
No, the minimum of the auxiliary. So the auxiliary array is storing indices of subtrees. So the minimum in the auxiliary array, the minimum is this number 1, meaning that the smallest value is stored in child 1. The actual smallest value could be like the square root of n plus 20 in that tree. Okay. Okay. All right. So and now we set x to w dot min because we're going to still have to pull x out of that subtree. And then, of course, there's a case where if x is w dot max, then, well, we've got the same issue. We're about to get rid of the max. We need to replace it with something. Where do we find it? Well, we look for the largest, the largest indexed child that has something in it, and then the largest thing in that tree will be the largest thing that's left. So it's the second largest value right now, but we're about to delete the largest value. So j then gets w dot ox dot max, w dot max gets w dot child at j dot max. Good. then x gets w dot max. All right, we're not done yet. We haven't even deleted anything. But now we're set up. We've dealt with the min and max. They're all, everything up there is correct and fine, but we still have a value x that needs to go away from some subtree. What is the subtree that it's in? It's the subtree I gets x over square root of n. And what do we want to do? We want to remove x from that subtree. So that is remove x from w dot child at I. All right. Are we done? Same issue. We just reached into one of our children and removed something. There's a danger that it was the last thing in that tree. And so we need to check if that happened. So if w dot child at I dot min equals w dot child at I dot max equals -1, which is what happens when we remove the last thing, then we need to remove I from w dot aux. Because that ith child is now completely empty. We need to take it out of aux. All right. So again, all of this stuff is constant time. There are two recursive calls, this one and this one. That looks like bad news, but we can do the same thing we did before. If we make the second one, it's only because we just emptied the ith child. So we can go back and look at what the code looks like when the ith child gets just emptied. That is when w dot min dot w dot max is x, right? We just took x out. It was the only thing there. In that case, we set it all to -1 and we return. So that takes constant time. So if we make this recursive call, then this one really only took constant time. And otherwise, if this one really is a recursive call, then we don't make this one at all. So same recurrence. T of n is a constant amount of work, plus we have to run the same algorithm over a universe of size square root of n. So there you go. All three operations, each of them running in log n time, worst case time for operation. So again, that's really incredibly impressive, right? I mean, this can be, well, I mean, the size of this set is, the size of the universe can be this, 2048. The size of the set, how much of it we're storing, doesn't matter. That doesn't affect the running time at all. It's just the size of the universe that matters. So no matter how many of these elements I'm storing, I'll get done in 11 levels of recursion for adding, removing, or searching. So very impressive. The space requirement is not terribly impressive. It turns out if you do it carefully and instead of using a giant array for the children, you use a hash table, you can get this, show that the space is n log n, I think, something like that. So it's not terrible, but we'll learn how to do better soon. All right, so that is a great place to stop today. I don't know if there's another class coming, but I keep getting in trouble for staying here too long. So we've got to run out of here now. Thank you.